All right, here's solutions for perfect problem 6 for Math 243. This is our introduction to hypothesis testing. So when you're doing hypothesis testing, the basic idea is that you're going to have, well, let's read through the problem. I claim that drinking coffee enables me to write quizzes faster. Faster will be a key word later on. I know that a quiz normally takes me 15 minutes to write. So what this is saying is that in the absence of coffee, just normally, the population average is equal to 15. You might think that we use mu for that population average, which we actually don't. We use mu naught, mu with a little 0 next to it. Something like that. Why? Why mu naught instead of mu? Because we're saving mu for something else that we're going to use later. So I know that normally a quiz takes me 15 minutes to write, but in a random sample of 35 quizzes, sounds like a sample size, so n equals 35, which I wrote while drinking coffee. The average amount of time it took me to write a quiz, so this sounds like a sample average here, was 14 minutes. Sample average, we use x bar to represent. And my sample standard deviation was 4. Test the claim that caffeine decreases, so that kind of coincides with this faster from earlier, the amount of time that it takes me to write quizzes, with 95%. Tells me that alpha is equal to 0.05. 1 minus 95%. Confidence. And we're supposed to do it twice, using the p-value method and the classical method. Okay, fine. Okay, so let's get started. State the null and alternative hypotheses. I think it's easier to state the alternative hypothesis. The alternative hypothesis is the claim being made. So in this case, the claim being made is that coffee decreases the amount of time that it takes me to write a quiz. So for H1 right here, I'm going to write coffee decreases the amount of time that it takes me to write a quiz. However, that's a little bit wordy. It would be nice if we could write it in symbols. It turns out we can. And it looks like this. Okay, so what this is saying, mu is the population average. Note, not the population average just normally without caffeine, but down here it's the population average if I always drank caffeine, if I was always drinking coffee. And my claim is that mu, this population average, is less than 15. Because it's less than, this is a left-tailed test. You don't have to write left-tailed here, but it can be useful for later on. My null hypothesis is always that mu equals mu naught. Mu naught in this case is 15, so I say mu equals 15. Typically, you're not going to describe what a type 1 error is, but since we're just learning vocabulary, I'm going to state it at this point. Because you can get the type 1 error from the null and alternative hypotheses. Type 1 error essentially is a false positive. It's when you incorrectly reject the null hypothesis. So in this case, the null hypothesis is that coffee does not change how much time it takes me to write a quiz, that mu is still just 15. If I rejected that hypothesis, I would be concluding that coffee makes me write a quiz faster. So if I incorrectly reject it, what I'm doing is concluding that coffee decreases quiz time, quiz writing time, when in fact it doesn't. As I said earlier, kind of a false positive. I'm concluding that coffee works, but it really doesn't. That's what a type 1 error is. Okay, so describe / justify the shape center spread. We've been doing this for a while, so these won't be any huge surprise to you. For shape, better be approximately normal, because otherwise there's nothing I can do in this class. It is. The reason why is our central limit theorem, which says that as n gets larger, the shape of the sampling distribution becomes approximately normal. In our class, we say it's approximately normal because n is greater than or equal to 30. Center. Okay, you can get a little bit lost in symbols here. I'm going to say mu sub x bar. So the average of all the sample averages. That thing's just equal to mu. Problem, we don't know mu, but the logic of these hypothesis tests is we start out by assuming the null hypothesis is true. We start by assuming mu equals 15. So for the picture I'm going to draw, when we assume that this is true, I can say that mu equals 15. Spread sigma sub x bar. It would be nice to use sigma divided by the square root of n, but I can't because I don't know sigma, so I have to instead use s divided by the square root of n. S was given to me in the problem as 4, n 35, so I get 4 over the square root of 35. And with this information, I can do everything I need to run my hypothesis test. So the first picture I'm going to draw, maybe I draw it over here, corresponds with the hypothesis test using the classical method. Okay, so when you're drawing the picture here, okay, I'll just talk through it as I go. My center is 15. And what I want to do is I want to draw my rejection region. And so what your rejection region is kind of the area where if your test statistic falls, you're going to reject the null hypothesis. I'm going to draw a region only on the left side of this distribution. Why the left side? Because this is a left-tailed test. The total area of your rejection region is always equal to alpha. So since I only have one rejection region, this area has to be equal to alpha. I decided earlier that alpha was 0.05, so this area is 0.05. What I need to decide is what point goes right here. Kind of. And you can figure out what point goes right here by, well, there's two different ways. You can either use a calculator. This looks like a problem that we've done earlier in this class. Earlier in this class, when you're given a probability, you could figure out that the point that corresponds with that much area below it by using the inverse norm function on your calculator. Unfortunately, we can't use inverse norm here because since we don't know sigma and instead are using s, this is a t distribution, not a z distribution. So we'd have to use the inverse t function. Some calculators have an inverse t function under this distribution menu. It's like the 5th or 6th thing in here. Mine doesn't. It doesn't say inverse t anywhere in here. So that leaves you with two options. You can either program an inverse t program. There's a description of how to do that on my website. I don't have it in this calculator. So all that leaves me with is I can look at my tables. To look at your tables, you need to know the degrees of freedom. The degrees of freedom are always 1 less than n. So since n is 35 and I want 5% to be the area in the tail, what I do is I go to my t distribution. Maybe I can zoom in. Degrees of freedom were 34. Tail probability is 0.05. So let's see, somewhere between 30 and 40, you can use either of these two values. 34 to me is closer to 30, so I'm going to use 1.697. This value right here, 1.697. If you use your calculator, you might get a slightly more precise value. 1.697 is not in terms of minutes that it takes me to write a quiz. It's a z-score. So z-scores, the middle is always 0. So really the center of my picture would be 0 in this case, and this score would be out here. You can write it, you can figure out how many minutes that would be if you wanted and write it up on this line, but I'm not even going to bother. I'm going to draw my picture like this, put the 1.697 right here, and then get my test statistic by comparing it with 1.697. So what I'm saying is to figure out what my test statistic is, I'm going to use tests, and then I'm going to run a t-test. T-test because this is a t distribution. It's a t distribution because we don't know sigma. We instead use s. So if I click t-test, it'll say, all right, you can run a t-test whether you have data or statistics about the data. I don't have the raw data itself. I don't have, it took me 8 minutes to create a quiz. One time I was drinking coffee, 12 another time, 22 another time. I have statistics about the data. So what it asks for is mu naught. I found mu naught earlier to be equal to 15. X bar. I found x bar to be equal to 14. S sub x, the standard deviation, which was given to me as 4, this value right here. And then n, which we know is 35. And then finally it asks me, what is your alternative hypothesis? That mu is not equal to 15, mu is less than 15, or mu is greater than 15. In this case, our alternative hypothesis is that mu is less than 15, so I'm going to get this second guy here. And then you can either calculate or draw. Doesn't matter. Either one will give you your answer. Draw is kind of cool. It shows you a picture of what's going on. Sure, let's do that one. What it's going to do is it's going to draw this thing for me right here. slowly. Actually, really what it's going to do is it's going to draw the picture for the p-value method. So it's going to kind of draw the picture for part 2 that I'm going to end up doing. So although you could get all the information you need from here, I think you don't really need this picture. I think what I would instead do is when you're doing the classical method, go back down to t-tests. Instead of doing draw, let's just do calculate. All right, so what this tells me is that if this is your alternative hypothesis, the test statistic is negative 1.479. I got a problem here. This should have been negative 1.697 because if 0 is in the middle, 1.697 negative would get me to this critical value. So this point right here, kind of the cutoff for my rejection region, is negative 1.697. Negative 1.48 is between 0, it's between these two, somewhere in here. Negative 1.48. This is my test statistic. My test statistic is not in the rejection region. So what I have is sketch a distribution showing the critical value. This is the critical value right here. This is the test statistic. And then this is alpha up here. Sketch a distribution showing all that stuff. Draw your conclusion. So my conclusion would be because my test statistic, which is this negative 1.48, is not in the rejection region, and it's not in the rejection region because to be in the rejection region it has to be further negative than negative 1.697, and it's not. Because my test statistic is not in the rejection region, there is not sufficient evidence to reject the null hypothesis. I'm not saying the null hypothesis is right. I'm not saying that coffee has no effect on how long it takes me to write a quiz. What I'm saying is there's not enough evidence for me to conclude with 95% confidence that coffee does in fact decrease the amount of time it takes for me to write a quiz. So I'm not saying it's innocent, I'm just saying it's not guilty, I guess is the way you could think about it. If guilty means coffee makes me go quicker. Here's my conclusion. That's finally the end of part 1. Fortunately, part 2 will go quite a bit faster. For part 2, we're using the p-value method. And when we use the p-value method, the null and alternative hypothesis are the exact same. The shape, center, and spread are the exact same. So all we got to do is draw a new picture and restate our conclusion. Our conclusion we'll come to the same conclusion as we did before, just for a different reason. So I still have 15 in the middle, but below it I'm going to write a 0 because all the information will be given to me in terms of z-scores. And what I'll do is I'll come up here and do stat tests. Actually, I had all the information in that last screen, but I kind of like looking at draw for this one because when I hit draw, it draws me exactly what I should do here. And so it gives me this curve. Its curve is a lot prettier than my curve. But what it will tell me, if you look up under p-value, it says make sure to show the test statistic and the p-value. Those will be the two things that this tells me. So the test statistic, as we already know, is negative 1.48. It'll show us that in just a second. There it is. My test statistic is negative 1.479. And then it also gives me the p-value. This p equals 0.0742. What the p-value is the probability of getting a result as extreme as your test statistic. So as extreme in this case means the area to the left of it is this p-value. But if it were a two-tailed test, I'd have area on both sides. But in this case, it's just one-tailed. So what this is saying is my p-value is equal to 0.0742. And my test statistic is equal to negative 1.48. And the way you draw your conclusion when you're doing p-value testing is you compare your p-value and alpha. And anytime your p-value is greater than alpha, like it is in this case, because 0.07 is greater than 0.05, because my p-value is greater than alpha, there is not sufficient evidence. Same thing I said above. To reject the null hypothesis. So quick summary, had my test statistic been in the rejection region, I'd say there is enough evidence to reject the null hypothesis and conclude that coffee makes my quizzes go faster. Similarly, had my test statistic been in the rejection region, then if I had done things the p-value method, my p-value would have been less than alpha. And the reason that's true is because the p-value is the area to the left of this point, negative 1.48. So if this value right here is smaller than this value, that means this line is further to the left of your critical value. So they're telling you the exact same thing. If your p-value is less than alpha, you reject the null hypothesis. If your test statistic is in the rejection region, you reject the null hypothesis. But those things did not happen. My test statistic was outside the rejection region, which is equivalent to my p-value being greater than alpha. And in that case, you just say there's not sufficient evidence to reject the null hypothesis. You don't say the null hypothesis is true, you just say it's not false. That is hypothesis testing. That's what we'll be doing for the rest of the class. So I guess I'll end this long video here.